Hello, this is Mr. White, and this video is on definite integrals. Here are the two exercises for today. Okay, so at this point in the course, it's quite normal for students to get a little bit frustrated and overwhelmed. You're just told recently that this symbol means to antiderive. And then you're told that when you put little numbers here, then it means take the area underneath the curve. And then we go through this crazy process involving limits and sigmas to find areas under the curve. And now you're being told that yes, sometimes we go this route, sometimes we don't. So if it's all a little confusing right now, don't worry, the puzzle pieces will start falling into place soon. But just keep this general rule in mind. When you're trying to find the area under what I'll call a curvy curve, like a parabola, then there is no geometry formula. There's no formula that you learned back in geometry class that will help you find that area precisely. However, when you are taking areas under something like a line, then you can look at that shape and say, you know what, I have a geometry class formula that helped me find that kind of area. So throughout the rest of the course, when it comes time to find a so-called area under the curve, you'll want to keep that in mind, that many times we'll need calculus, but other times geometry will suffice. And this is one of those times. In this case, we're flat out told to use a geometric formula, but most of the time in the future you won't be tipped off. You'll just be expected to know that. So if we're going to find the definite integral, which you now know represents the area under a curve in layman's terms, we need to come up with a picture, a sketch, as we were asked to do, to help us figure out that area. So let's rely on our pre-calculus skills, and this might be a case where you want to use some graph paper. So let's start with our basic function of y equals x squared, and draw that on our page. And let's think from our pre-calculus perspective. If I expand our view to now focus on 1/2 absolute value x, what does the 1/2 do? Well, it's a vertical shrink, right? So if I look at some of the points, for example, this point and this point would be convenient ones, here and here as well. If I look at those points and ask how does the 1/2 affect it, they're going to be reduced down to half of what they originally were. So we now have a curve that looks like this. And then we'll expand our view a little further and say, what about that negative in front of the 1/2? Well, that's going to flip or reflect across the x-axis. So now our graph looks like this. And finally, I say, okay, what about this 5? Well, that's going to move everything up 5 units. So we'll now have a graph that looks something like this. And we understand now that our definite integral, which is what we call it when the integral has these numbers here, we now understand that we are to take the area under this curve that we just drew between x equals -2 and x equals +6. So I can't emphasize it enough. Keep in mind those pre-calculus transformation skills. It always saddens me every year how many students kind of stumble over this kind of question. Now let's put in the -2 and the 6. So we're going from here all the way to here, assuming that the interval on this graph paper that we're counting by ones, 1, 2, 3, etc. And at this point you have some options. You could just count the squares on the graph paper, right? You could use the trapezoid formulas in geometry and say there's a trapezoid, there's a trapezoid. I find most students are most comfortable dividing this into rectangles and triangles. Try to be as efficient as possible in that. I sometimes see students doing way more rectangles than they need to, and sometimes it's not clear to me at all how they decided to split it up in that way. So what I'm inclined to do here is say, here's a rectangle, let's see, here's another rectangle, And then we've got two right triangles, one up here and one here. However you choose to divide it up, on a test, make sure that you clearly draw and clearly label your picture. If I just see a bunch of numbers scribbled over here off to the side and I can't tell how they relate to the picture, it's going to be awfully hard to give you credit. And if you choose to go the triangle and rectangle route, the area is easy enough on that where I might just do this. Say, okay, this first rectangle is 2 units by 4 units. So I might just draw write the area inside. This one is 6 units by 2 units. So that's going to be 12, right? This smaller triangle up here is 2 units by 1 unit. So 1/2 base times height will give me 1 square unit. And then here we've got 6 units by 3 units. 1/2 of 6 times 3 will give me 9. So 1 plus 9 gives us 10. 8 plus 12 gives us 20. Our area is going to be 30. Now think of how sad you would be if you were not prompted to use the geometric formula and sketch the curve, and you ended up trying to do some crazy limit process on this. And first, do the absolute value bars, you'd have to split it up into a piecewise function. It'd be a big mess. So take advantage of those geometric formulas when you can. And of course, you could use the graphing calculator to confirm your results. Okay, let's get on to the next one. So here we are to evaluate this definite integral given these two values. And once again, get the limit and summation process out of your mind. And in fact, the process we used in the last exercise of using geometry formulas, even that's going to be useless to us here, because notice that we don't know much of anything about f of x and g of x. We have no idea what they look like. The only thing we know is that when you take the area under f of x from x equals 5 to 10, you'll get an area of 4. And when you look at g of x from 5 to 10, you'll get an area of 13. That's all we know. So the purpose of this type of exercise is to see if you're comfortable, if you know what kind of processes you can and can't do with definite integrals. And the good news is that they will feel what you can and cannot do. The rules are fairly similar to derivatives as well as summations. So with derivatives and summations, you are allowed to take constants to the outside. So this 2, for example, could come to the outside in the form of 1/2, since the 2 is in the denominator, right? With both derivatives and summations, if you had something minus something else, you're able to split it into 2. And a derivative of one function plus the derivative of the other, or a summation of one expression plus the summation of another. So with that in mind, let's proceed to split this one up. Now let's see what's affecting this f of x here. If I have an integral from 5 to 10 of f of x, I see up here that there's a 5 and the 2 are both applied to that f of x. And so I'll bring both of those constants to the outside as a 5/2. I now turn my attention to this g of x here. And I do an integral from 5 to 10 of g of x. And this minus sign and that 2 are affecting it. So I'll do minus 1/2, the integral of g of x from 5 to 10. And what about this plus 7 out here? It doesn't have anything to do with either of those functions, but I'll still just add an integral from 5 to 10 of 7 dx. So at this point, it's a pretty straightforward substitution. This integral, we are told, equals 4. This integral, we were told, equals 13. So we'll apply those other numbers there, 5/2 minus 1/2. And as far as that last integral goes, think of what that looks like. Think of what y equals 7 looks like as a graph. It's just going to be a horizontal line up there, 7 units above the x-axis. And we're going to take its area from 5 to 10. So if here's 5 and here's 10, and when we think what's the area under that curve, the answer becomes pretty clear. We're dealing with the rectangle. a rectangle that is 5 units long by 7 units high. So 35 would be the area, right? So that's what we'll add for the definite integral. So let's practice our mental math here. 5 times 4 divided by 2, that's going to be 10. Plus 35, that would be 45. And then 13 over 2 is going to be 6.5. So I've got 45 minus 6.5. That's going to be 38.5. So we'll put 38.5 and call that our final answer. Unfortunately, with so little information given about these functions, there really is no way to check this via calculator, but as long as the work is all clearly shown, we can at least be confident that we'd get most of the credit, right?